In Chapter 17, we'll finally start talking about benzene and aromaticity. If you remember throughout the course, we've been talking about the 5 keys to organic chemistry, and the way to remember them is areas. So with A, we have acid-base, R is resonance, E, electronegativity polarity, second A, aromaticity, and S, sterics. So the 4 of those we've been talking about a lot already: acid-base, resonance, electronegativity, and sterics we've been talking about a lot already. Now we're finally going to look at aromaticity in this chapter. So first we better talk about benzene and what benzene is. Benzene is molecule C6H6. It's really the simplest of the aromatic compounds. It has 4 degrees of unsaturation. Often it's drawn like this. So our 4 degrees of unsaturation are 1 ring and 3 pi bonds. Now what makes benzene interesting? Well, we've talked about a lot of alkenes before, and so the pi bonds shouldn't be anything new to you. And we've done reactions like this. If I take an alkene and react it with Br2, I get a dibromo compound. One would expect then that if I take benzene, that has 3 double bonds. Before I only had 1 double bond, but now I've got 3 double bonds. I would think that it should be pretty easy to do this reaction and get at least one of the double bonds to react to form the dibromide. And instead what we get is no reaction. Why is that? It has 3 double bonds, so it should be really easy to get one of them to react. But instead it doesn't react at all. However, we can do a similar reaction and add a bromine. This bromine adds through a substitution reaction, while the one up here was an addition reaction. That's our first clue that there's something completely different with benzene than there is with other alkenes. So it's not just a molecule with 3 alkenes in it. There's something different. We'll continue to see that throughout this chapter. Kekule suggested in the late 1800s that benzene was actually a rapidly interconverting pair of structures that have alternating single and double bonds. Now we know a lot more about how resonance delocalization works, and we realize that any resonance structures are not rapidly interconverting, they're both things at once. The reality is that benzene is actually a resonance hybrid of the 2 structures, both at the same time. So how can we really determine whether that's true or not? Well, let's look at bond lengths. So if we have a carbon-carbon single bond, carbon-carbon single bonds are typically about 153 picometers long, while carbon-carbon double bonds are 134 picometers. When you do X-ray crystallography, what you see are the positions of atoms, and you can easily measure the bond lengths between them. We would run an X-ray crystal structure of benzene to see which bonds are single bonds and which bonds are double bonds. And when we do that, what we find out is that all the carbon-carbon bonds in benzene are 139 picometers long, which places them at somewhere between a single bond and a double bond, so we call them all 1.5 bonds. We could add a dashed line. If we wanted to look at a resonance hybrid structure of benzene and say, okay, there's 6 electrons in here, and they're all equally shared around the ring. Sometimes we'll draw benzene with a circle in the middle, signifying that the electrons are all shared all equally around the ring. Quite often we'll draw benzene just showing one conformation, like with many other things that we do with resonance, recognizing that that's just one of the resonance structures. Other things about benzene we find out from the X-ray crystallography is that all the bonds are 120 degree angles, and that benzene is flat. It's completely flat. So it's different from cyclohexane, which would have a chair structure.